Alright, so this is week 6 and we're talking about components. This is an overview of some of the components you will see in the field, in the HVAC field. I'm talking about solenoid, and we said that solenoids are, what's the fuel over there? What in that? Okay, talk about the solenoid, and if you look at the solenoid, it's basically a big electronic magnet. We run amperage to it, and it will pull in a pin, push in a pin. What would you think the strength of this magnet depends on?
Current.
Huh?
Current.
Current, excellent. What else?
Windings.
Windings, thank you very much. So two things. The strength of this solenoid depends on the current that goes through it and also the winding. So if we lose some of this winding, it gets cut, part of it gets destroyed, you will not have the same amount of magnetic field around it. So this is one way to test it. We test the resistance of this coil. And if you notice, what color is this coil? It's kind of red. What would you think is the reason of this color? If you look at the wire, copper is usually kind of light red. It's dark red. So what is on this wire? No. Yes.
Copper.
No, it is copper, but why is it so red?
To see it oxidized.
No.
Pure.
No. Say what?
Pure.
No.
It's colored.
Okay, why is it colored?
Does it
No.
act like an insulation or something?
Yes, it's insulation. So there's very, very thin, waxy or tar insulation. So we do not want each wire to connect with the other one. We want each wire to have its own magnetic field. So this insulation made out of wax or tar to insulate the current from each two wires because they are stuck together. Okay. So what would you think? Some of the reason that this thing will break?
The wax melts.
It melts because it's overheated. Sometimes it oxidizes with the moisture and becomes different color. So visually you can inspect to see if it's all the same color and consistent. You know it's a good coil. If not, probably has been melted or has oxidized with air. And if you look the same thing here at the relay, let's look at the bigger relay. There's also a coil here, so you can test the coil for resistance. And sometimes you should say on it what is the resistance of the coil. This one it doesn't, but this one tells you what is the voltage that goes through it and what is the amperage. So this is one way is to test the coil and see if this coil is continuous. You're not supposed to open a relay, you just change them. So coils are very important to pull in armature or pull out pins. Talk about heaters, and we said they are there to heat a certain area. It's a very effective way and fast way to heat defrost cycle, in the defrost cycle in the fridge or the freezer or ever in the AC. If you look at the AC evaporator, which is inside, sometime in a humid day it will start to accumulate some ice, and that's not good because that will prevent the flow of air going through. So if it's ice, probably there's a sensor on the evaporator that will activate the defrost cycle. Shut off the compressor and warm up a little bit of that ice. You'll see the same thing for ice machines, same thing for big ACs.
So that's why every year you have to clean out the freezer, or not clean out the freezer, but defrost the freezer?
Yeah, that's the old freezers, not anymore. Not anymore, yeah. They make it mostly automatic now. And most freezers actually, every time you open it and you close it, you hear something like vacuums and sucks all the air out. And then by doing so, you will get the moisture all out of the system. Also, if you look at ice machines, what does it do? It runs refrigerant through the evaporator until it starts icing. And then the sensor, once you reach the ice thickness, it will activate. Once it activates, that little blade where you're accumulating the ice will start heating up, and this is how the ice breaks and falls down. This is the whole idea of an ice machine. This is where we use heaters. It's electric resistance. That's what it looks like. If you see it in the schematic, probably it looks like a resistance. Why? Because it's basically a resistance. Very high resistance that generates heat based on the material. Huh? They look the same.
Yeah.
They all look the same.
It would.
Just that the purpose is to tell you that they all look the same. Here we've got resistances, and they're made out of sometimes manganese, magnesium, manganese, and sometimes tungsten. And now they have some ceramics. I think the ceramic is just for surrounding the heating element. That's what they look like. Signal lights, those are very important, and usually we put signal lights near components that's really hard to reach, and it is in series with the component. Why? If we think about the two things, is safety and control. So if the light is on, means the circuit has power. If the light is off, means it doesn't have power. So they come in different colors. Sometimes we have regular lights, and sometimes we have LEDs. And what happens is, again, it's just an indication that that sub-circuit has some power. So you have combination circuits, parallel and series. You want to have every sub-circuit with a small light bulb. So you will know that this circuit is not functioning at all. We need something, because we do not see electricity, we do not see current. So we need something we can see, we can visualize to put lights. Yeah, question?
What were you saying about like the series? Like you put in a series?
Yeah, you put the light in series with the circuit because you want to know if that circuit is running or not. So for example, if I have a circuit for the motor, this is my motor circuit. If I put a light bulb with it, go back, voltage. So if the motor is getting power, the light will be on, right? So you have to put it in series, not in parallel. If you put it this way, even if the motor is not getting power, probably the light will be on. So you put it in series with the circuit to know if it's running or not. It's a good indicator for the system. Is it getting power or not? And probably you'll see a lot of LEDs in the field if you work with power plants. Usually they will see a lot of circuits. And sometimes you have an alarm, sound alarm, like a bell or a small beeping noise that tell you that this circuit is off. And the way they do the alarm is using a relay. And I will explain why in the same manner here. So I'm gonna put a relay here. Just look at that relay. So if the system is energized, this coil will pull in the armature, and this system will be off. Once this system cut off, it's not functioning, this will lose power, the armature will close the circuit, and you have light. So the light here indicates that the system is off. Question?
What is a relay?
What's a relay? That's a relay. So a relay, we'll talk about relay for entire chapter. But if you look at this relay, you see a coil, right? See this little armature? They're doing connection between those two sides. So when it's energized, it should pull or pull, depending on the design of the relay. And it connects two circuits together. Like here, if you put this relay, this circuit here, if it's energized, it's gonna be open. It's normally open. And if we de-energize it, it will close the circuit, close an alarm.
So are they like used to like show that the circuit's not working?
They're used for control, depending on the relay. It's normally open, it's normally closed, and mostly for control and communication between two circuits. If you close this one, then open this one, and the other one. If you look at this one, it has at least one, how many pins? 1, 2, 3, 4. So 4 terminals, so it does 4 things at the same time, based on the inputs here. 1, 2, 3, 4, 5 inputs, based on one energized G-energized. So probably to close one thing and open 3 things, or whatever design it has. So, and it should tell you here, is it normally closed or normally open? And you'll see that again when you do the primary control. Once we lose fire, system will shut off. It will shut off all components and it will turn the alarm. So one will be on and 4 will be off, based on the loss of light. But we'll talk about that in more details. These are contactors and relays. So they open and close one set or sets of electronic contacts by actions of a solenoid coil. Everybody get the chance to look at this? Want to look at it again? This is the relay and the coil. If you try to imagine, let me put it in the dot camera so you look at it.
Rod, after this, can you go back to that slide?
Yeah.
It's on page 89. Yeah.
Can you see this clearly? So if you follow, this is really nice because it's very clear. You can see what's happening inside. If you look at those 2 pins here, they are connected to the blue line, which goes into this coil. So once this is energized, this coil will be energized and will have a magnet, and it will do this pull action here. And what it does is going to pull these 2 pin armature over here towards it, and that will connect them together. And if you look at the second connection here, so these are connected to here, the first one, second one connected all the way from here to here. And if you look at the top, there's also another connection here in the board. So this will open up and this will close this connection, and this connection will also be pinned, and this one will be disconnected. So we have 5 terminals here between 2 connections. So this is the first one connection and this is the other. These 2 will connect together if this one is energized, and these 2 will connect together if this one is energized. So it's don't overwhelm yourself as long as you know what is the basic idea. A coil, control, armature, and this is way too many of those. Let's look at the simpler one. This is very, very simple. So we have these 2 connections. You see them? These 2 connections, these pins in the bottom, and the other are for the coil. So once the coil energized, it will pull this metallic part in, and that will push those. You see how the pins are connected to those ones? So those are normally closed. So they're closed now. You agree? See how it's touching? Yeah. So these are closed. It's normally closed. Once we energize this coil, they're going to be open, and this one will be closed.
Couldn't you energize that with a battery?
Huh?
Couldn't you energize that with a battery and 2 cables?
I need
To see how it works?
120 volts. Yeah, I can connect that and show you how it works. I'll do it next class. I'll show you how it connects and disconnects. So, and the connection we have is this one. So this now is it connected or not? Let's look. So these are connected to here and here, and they are connected with these 2. So these 2 are connected now as normally open. Normally closed, it will disconnect those 2 and connect these 2 in here. And it's still the same energy. I'll show you how it energizes.
So it's bad because it's open now?
Huh?
Is it bad because it's open now?
It's not bad.
Oh, okay.
No, it's good, but it's just like, as it is open, these are connected by default.
How would you know if one was bad?
Good question. Does it shake? One of those armature will break? That's actually a good question. It's going to be in the quiz 4 or 5. So how do you know it's bad? First of all, you look at the coil. You can test the coil. So let me test the coil. And realize that I'm not cheap. They are not cheap. So how do we test the coil? We put it on resistance. I will test the coil. It's giving me something. So it's continuous. That's good. So are these, would you think these are continuous or not? What about these two? You think they're connected or not? By looking at it.
No. No, it is, it looks connected.
Huh?
It looks connected.
Let's find out. They're not connected.
No.
What about these two? See how it's, can you see it?
Yeah.
See how they're connected now? I'll test them. They're not, something has been connected. Oh, I'm putting in the,
So what, if it was bad, it had zero resistance?
yeah. What do you think could happen besides breaking of the armature or the coil?
Fry the windings.
That's one thing, that's the coil.
Burn out.
Is there some kind of fuse inside there?
Huh?
Is there some kind of fuse inside there?
Connection here is bad. So this, did you just give me resistance before? Okay. No.
Only the first two ports?
This is a bad relay because it's not connected. This is supposed to be connected. So we mentioned two things. Either the coil is bad, the armature is bad, or what else do you think?
Are you hot enough to weld in one place and just stay?
Possible, which is what's happened. You see this little dots in here?
Ah.
These here.
Yeah.
These little metallic parts made out of silver, and it looks like a dome. That's what they look like.
It's supposed to be touching?
It's supposed to be touching, but do you know if they have contacts or not? So this is what it looks like. That is very important, by the way. So one thing, Rene said that they could be welded together and stuck. They're not moving back and forth because if you look at the armature, it's very thin. It's supposed to be having the lowest resistance possible. So one thing they get stuck, the other thing is they oxidized. They're not making connection. The surface area between the connection here is really thin, and that's why they're made out of silver, which is a very good conductive material. But over time, if these things get some air into it, it will oxidize, and there's no contact between them.
So
they're touching.
it basically works as a flint, like a lighter, the two contacts together.
Yeah,
push
he's touching.
electricity
Yeah.
Towards each other.
So this is one of the things, and they have something called contact cleaner, which does that. But this is one of the common issues with mechanical contacts. What are the other type of contactor you have, relays? You have electronic ones, which it's much better than these, but they don't have the same kind of voltage, so they have very small voltage.
Drones.
We'll spend the whole week on talking about contact and relay because they're very important. How do we read them and how do we know the action? Because as you see, there's a lot of pins. Sometimes they connect and disconnect. Questions? So what is the difference between a contactor and relay? Probably Bill said that. That size. It's the amount of amperage that goes through it. Any contactor is more than 20 amps. Any relay more than 20 amps, it's a contactor, and that's what the book says.
Relay is less than 20.
Yeah. What page is that?
Over 20 amps.
89.
Contactor.
Huh?
You said over 20 amps.
Yeah.
Contactor.
Write that down and it's in page 89. That's the difference. So it's just terminology, they're all relays. They all do the same thing. You go with this?
No.
So write it down. Page 89, it will tell you what's the definition of a contactor and a relay. A contactor is very large. Probably it's with a. There you go. That's a contactor. See how big it is? And you'll hear. You hear the click. It's a very strong click. The magnet is connecting those two. That's when you switch your thermostat and you hear the big click. I'm gonna do it right now and you will hear it. It's very big click. Cooling. Hear that? That's your contactor activated. The first bang, then the compressor engaged. Now you see how,
So it's like the starter to a
Yeah.
car.
so one of the problems you also get with the AC contactors is some bugs get in the middle. See the contact in the middle? And you see the contacts over here, so these need to be cleaned. You don't have to use sandpaper. That will ruin the surface, cleaning with solution. So I'm gonna pass those through. You can look at it. That's a big contactor for an AC, and that's a relay. And if you look at the size here, it should say on it something less than 20
I
amps.
feel like I'm back in the 1800s sending a
It
letter.
still functions. Does this picture look familiar now? What is this?
Circuit.
No. What does it represent inside the relay?
Solenoid.
The coil. Solenoid. Thank you. And these are the contacts. So these contacts here are normally open, closed. These are normally open. What does normally mean?
Before you even started.
Thank you. Thank you. This is what it means. Normally open. You hold it outside, it's open. Once you energize it, things will change. We'll practice that a little bit more. And this is a contactor for a general AC. And it's good to know how to read those little pins. They make it as simple as possible because you want to know which pin goes where. Did you do the board with Bill for the AC? Probably not yet. But you'll see how intricate it is because you have high voltage and low voltage control. And you don't want to mix them up because we have 24 volt for the control and 110 or 220 for the compressor. So you want to know the right voltage. And the reason the contactor is big, it handles a lot of voltage going through it. So 3 parts: contacts, and coil or solenoid. This is the coil. A mechanical linkage. This is the mechanical linkage. I'm going to write it down. So it communicates 2 circuits together. Any questions?
Please say that one more time.
These are the contacts.
No, you said they connect.
They connect 2 circuits together. They help 2 circuits communicate with each other. If you believe it or not, back in the days, the mainframe computers were just a set of contacts. That's why it wasn't big as a room. Small contact with each other. And you imagine the power that is required to supply to all those little magnets, it's a lot to make a simple calculation. And if you did any kind of logic control, it was a combination of kind of gates, decision making gates, and or I'm not going to go into it, but anyways, basic computers, early computer used a bunch of contactors to make decisions. So normally, position of set of contacts when the device is de-energized, as David said, normally open. Set of contacts that are normally open when the relay is energized and contacts are closed. Normally closed, set of contacts that's normally closed when the relay is energized, contact open. Write this down. It's in the book, but this is very important. Especially when you try to change a relay. If you don't have the same part number or model, probably it will be confusing to have their own relay. You know contacts and relays now? A little bit? They have a whole chapter about how to read them, how to get the right size, and how to connect all the poles. Normally closed, normally open. Good? A lot of these things are very difficult to talk about, but once you start working with them, it will make a lot of sense. But at least keep some of this stuff in the background of your mind, so when you work with them, you can recall some information. But it's easier to just work with them than to talk about it. This is the symbols, if you see it in the schematics. This is symbol normally of open call for a contactor. This is a symbol for it. And again, it differs from one book to another. So we'll see something like that for a relay. And that's normally open. This is normally closed. But again, this is not everywhere. It could vary from one book to another. Relay or contactor coil. The coil either look like that. I like this one better because it looks like a coil. A circle could be anything. But you will see these two symbols. It will look something like that. That'll be a relay. Or you'll see something like that. Any questions? One more thing here is the magnetic star. What's a magnetic star? It's an evolved contactor. Contactor, this is like the contactor and steroids. Relay and steroids. It's really huge, it's very big, and looks as a contactor. However, it has overload protection. That's the only difference. So if this relay is rated at 30 amps, and suddenly we are drawing 40 amps, it will just break. So probably you'll see these for big ACs, industrial ACs. You'll see a lot, and it looks kind of messy when you look at it. But don't worry about that for now. These are the contacts, and these are the relays, and this is the overload relay. Don't worry about the schematic. What I need you to remember for now is it's a contactor, which means it's more than what? Carlos? More than 20 amps. What is the difference between a contactor and a magnetic starter? Overload protection. Yeah, this one has overload protection. What does that mean? If this starter is rated at 30 amps or 25 amps, if we run 40, more than one is supposed, it will break. Not break, it will cut off the circuit. To break the circuit. Make sense? Okay. Switches. A lot of components we have with switches. We have two types of switches, either break and close switches or toggle switches, which reverse the cycle from one place to another. So open and close control, some load open and close to control some load in an electrical circuit can be opened and closed by temperature, pressure, humidity, flow, or manual. Did we experience temperature switch? You all did. Remember that switch with the knob on it? On the board? We work with it.
Big metal one.
Yeah, the big metallic one with the big knob on it, that's a thermal switch. The red one with the seals on it, that's a thermal switch. Pressure switches? That up. Another blooper? Okay. Hold on, mister. Pressure, humidity. You can have a humidity switch. Do you know what any humidity switches? Have you experienced those? Probably you did. Your phone now, your smartphone, if you have an iPhone more than 5,
I think it's too hot.
or Samsung, like around 6 or 7. If it's too humid, it will shut off. Kill you.
I really like that.
You
said humid? I thought it was like heat. If it's more hot.
Enough humidity.
Then humidity now?
Yeah. Probably you never got it this humid, but try it, put it in the freezer and see what happens.
Oh, yeah?
For how long? It's not like I
Huh?
like for how long?
put it for 20 minutes,
Carlos,
some
do not put your phone in
moisture
the-
inside, it will shut off.
Open up your glass.
If you have a newer phone, probably they're waterproof, so it's not gonna happen, but for the older models, in the last 2 years, they have humidity sensor in there, because they don't want to fry the CPU. So it will shut off at high temperature. If you leave your phone dashboard in the summertime,
Yeah, it will.
it will shut off. If it's too humid, it will shut off as well to protect the circuit. If you drop your phone in water in the past, it will shut off before it burns. So you take it out, you dry it out, you might need to take to repair, but you did not destroy the memory,
Put it in
did not
rice.
destroy the CPU.
That's the best way to dry
So-
it. Put it in rice.
Those switches as well. Any questions about this component? I think we did a lot. Can you please go through the book and highlight the parts that you need to remember, especially the numbers? And Friday, we're gonna go over the homework, and I have some group activity where we're gonna divide you into groups of 4s, and we're gonna do sub-circuits. Circuits in parallel and series and calculations. And if you did it right, your group get an extra point in the next quiz.
So Friday will be for Tuesday.
Huh?
Friday will be for the Tuesday pass.
No, it's for the Friday, it's a different class. Okay, thank you.